Hello there, kids. This is Mrs. Future, and this video is exponential growth and decay. An exponential function is one that is written in the form y equals b to the x, b being a number, but b has to be greater than 0, and it can't be 1. So we aren't going to raise a negative number to an exponential, and we're not going to raise 1. Because if I raise 1 to any power, I always get 1. Now, if b is greater than 1, you have exponential growth. So if I raise 2 to the x, or 5 to the x, or 78 to the x, we're going to be growing. But if b is less than 1, and it can't be any less than 0. So between 0 and 1, otherwise known as a fraction or a decimal, if b is between 0 and 1, you have exponential decay. So if I took 1/2 and raised it to the x power or anything else like that, then it would be coming down, it would be decaying. So let me show you what a growth function and a decay function look like. Alright, here they are. This is your exponential growth parent function. And it is going to look like this. You have an asymptote, which is this imaginary line right here that your graph is never going to cross at y equals 0. And then it starts over here. We actually have an arrow on the end of this because it does keep going. It approaches and gets closer and closer but never touches. And then it goes up and up and up and up. And at 0, 0 to the x power, anything to the 0 power is going to be 1. And b raised to the 1 power will always be b, so this is always going to be 1b, and this will always be 0, 1, and then the rest of it follows. You can just make yourself a table to get the rest of it, but it will be growing. So our domain, negative infinity to positive infinity. It's always going to the left, it's always going to the right. Any x is okay. The range, 0 to infinity, because y has to be greater than 0. Alright, here's the exponential decay. Now, it looks exactly the same as the growth, only reflected over the y-axis. It starts up high and then comes down. I just missed that, but anyway, with an arrow and an arrow. And it also approaches an asymptote at y equals 0. It also has a point at 0, 1, and then at 1b, only now b is a number that is less than 1, so it's coming down. And we have our domain is all real numbers. Our range, again, is 0 to infinity. Alright, for our first example, let's graph y equals 3 raised to the x power. First thing we're going to do is make a table. Now, as we know, x could be anything, but let's just start with 0. If I raise 3 to the 0 power, I get 1. If x is 1 and I raise 3 to the 1 power, I get 3. If x is 2 and I square 3, 3 to the 2nd power is 9. If I have x is 3, 3 to the 3rd is 27, and that's going to be off our grid, so let's not go any higher. Let's go back down now. If x is negative 1, 3 to the negative 1 power. Remember, the negative 1 power means take the reciprocal, so 3 to the negative 1 is 1/3. 3 to the negative 2, remember that's the reciprocal of 3 squared, so that's going to be 1/9. If I had negative 3, that would be 1 over 3 cubed, 1 over 27. So it's getting tinier and tinier and tinier, but it will never go negative. It will never hit 0, and it will never go negative. So let's graph that. Alright, so I've plotted the points on my table, and I know that this is going to keep going up and up and up. And it's going to approach, approach the x-axis, but never touch it. So I'm going to dash in my horizontal asymptote, and that is required when you're graphing, to dash in your asymptote. And if I asked you what is the equation of the asymptote, it's a horizontal line through y equals 0. Here's another example. Now we're going to graph y equals 1/2 raised to the x power. So once again, let's make a table. When x is 0, 1/2 or anything raised to the 0 is always 1. If x was 1, 1/2 to the 1 would be 1/2. If x was 2, 1/2 squared would be 1/4. If x was 3, 1/2 cubed would be 1/8, and it'd be getting smaller and smaller and smaller. It's approaching 0. So let's go the other direction. If x is -1, and I take 1/2 raised to the -1, that means take the reciprocal. So 1/2 to the -1 is 2. If I raised it to the -2 power, 1/2 to the -2 power would be 2 over 1 squared, which is 4. 1/2 to the -3 would then be 2 over 1 cubed, which is 8, and so on. So now let's plot those points. And here they are. If we connect them, we are coming down, and we are approaching but not crossing an asymptote, once again at y equals 0, but you have to dash it in there. I didn't talk about it on the last one, but the domain of this, -infinity to +infinity, the range of this, lowest y value is 0, and it doesn't touch it because we have an asymptote. Highest y value all the way up to infinity. Now, for this function, just like any other function we've done so far this year, the transformations apply. So the basic format of that would be y equals, sorry about that, and then we could have a positive or a negative a, and then we have our b to the x minus h, sorry if you can't see that very well, x minus h up in the exponent, and then plus k. All right, so the negative, if a is negative, that's going to be your reflection over the x-axis. The value of a itself, if a is greater than 1, it's a vertical stretch. If a is less than 1, it is a vertical shrink. The b is the b in your function. So the b doesn't affect it, and that confuses people a lot. Because if b is 2 or if b is 17, that's not going to do a vertical stretch or shrink. That's part of your actual function. So the b and the x are not transformation stuff, just the rest of it. Now the h up there with the exponent, if I'm adding or subtracting something with the exponent, that's your horizontal shift. And remember, it's opposite the sign. And then that k after the function is your vertical shift. And here's something new. If the x in the exponent is negative, that's going to reflect your graph over the y-axis. So if you had b to the x and you know it looks like this, b to the negative x reflects it over the y-axis. It just takes it across like that. And the reason for that is because a negative exponent gives you the reciprocal. And so instead of a greater than 1, you now have the reciprocal of it, which is going to be a fraction that's less than 1, and it's going to turn into decay. So let's graph y equals -2 times, in parentheses, 1/3 raised to the x minus 1 power. So this 1/3 is part of our base function, our parent function, and then this x. So the only things that are going to change it are going to be that negative, that 2, and that minus 1 there. The negative is going to reflect it over the x-axis. The 2 will stretch it vertically, and the minus 1 should shift it left 1. So let's make a table and graph that. If x is 0, then I have -2 times 1/3 to the 0 minus 1. So I have -2 times 1/3 to the -1. That's -2. And then 1/3, because remember this -1 power does not affect that -2. But 1/3 to the -1 is 3. And -2 times 3 is -6. If x is 1, I have -2 times 1/3 to the 1 minus 1. So -2 times 1/3 to the 0 power. Anything to the 0 power is 1, so when x is 1, y is -2. If x was 2, we have -2 times 1/3 to the 2 minus 1. So 1/3 to the 1 power is 1/3. -2 times 1/3 is -2/3. We can see that it's decaying. It's growing, -6 to -2 to -3. The reason for that is because this is decay, but this negative reflects it. And so if I reflect a decay, it becomes a growth. So if I plugged in a 3, we would get -2 times 1/3 to the 3 minus 1. So 1/3 squared is going to be 1/9, so that'd be negative 2/9. And we can see that it is approaching 0, but it's not going to touch it. So let's put on the graph. So there's the points. We can see that we are approaching our same asymptote of y equals 0. And it's going to be getting smaller like that because of the negative in front. Our domain for this is still all real numbers. But our range for this, now our lowest is negative infinity, and our highest is 0, and we don't touch it, so we put a soft bracket. All right, this next example, we're going to graph y equals 1/2 times 4 raised to the x plus 2. So this 4 raised to the x, that's our parent function. That 1/2, we'll shrink it by a half. It's going to be squattier, fatter, shorter. I mean, it's still going to infinity, but it'll be fatter. And then this plus 2 will shift the whole thing up 2. And if I shift my vertical asymptote, my horizontal asymptote from 0, if I shift it up 2, it's now going to be up as well. So let's make a table for this one. I can start with 0. If x is 0, 1/2 times 4 to the 0 plus 2. That's 1/2 times 1 plus 2. That'd be 2.5. If x is 1, half of 4 to the 1 plus 2. Well, half of 4 is 2 plus 2 is 4. If x is 2, we have half of 4 squared plus 2. 4 squared is 16. Half of 16 is 8 plus 2 is 10. So I'm growing. If I had 3, I'd have a really big number. Let's go the other direction. If x is negative 1, 1/2 of 4 to the negative 1 power plus 2. So it's half times 1/4 plus 2. Half of 1/4 is 1/8, plus 2 would be 2 1/8. So it went from 2.5 to 2 1/8. If I had negative 2, I'd have 1/2 times 4 to the negative 2 plus 2 is half of 4 squared, so half of a 16th plus 2. Half of a 16th is a 32nd, so I have 1/32 plus 2, 2 and a 32nd. You can see that it is approaching 2. It's going to get closer and closer and closer to 2 instead of 0 now, and that's because of this plus 2 at the end. So let's graph that. All right, here's our points plotted. You can tell that it is coming down like this, and then it's going to be approaching an asymptote, which we must draw in there with a dashed line at y equals 2. Now our domain for this, still all real numbers. X can be anything, but our range, the lowest y value we're ever going to come up with is 2, and it doesn't touch it because there's an asymptote. And then the highest y value goes on forever. We could get it as big as we wanted. The last example that we're going to do in this video is example 5. If I give you a graph, I might ask you to find the equation. So we're going to look at this, and we're going to say, all right, it has a horizontal asymptote at y equals 0, and it is growing. So we know growth and decay. Our equation is y equals something times b to the x. That's our general equation. We're not going to worry about our vertical shifts because we're not shifted up. We're not going to worry about horizontal shifts. We're just going to use the basic equation y equals a b to the x. And we need to figure out what a and b are now. So what we want to do is take 2 points off of this graph. You want to start with the y-intercept. That's one point that you always want to use. And then you can use any other point on the graph that you can find. So if we start with the y-intercept, the reason we're doing that is because x is 0. So I'm going to plug in y is 1/2. I don't know a, I don't know b, and x is 0. And anything raised to the 0 power is always 1. So now I have 1/2 equals a, which gives us half of what we want, right? We want a. Now we need b. So we're going to use this other point here. And we're going to plug in a 2 for y now. The half that we already found for a goes here, times b raised to the 1 power. So 2 equals 1/2 times b to the 1. Well, b to the 1 is just b, And if I multiply both sides by 2, I get b equals 4. So now that I know a and b, I can write my growth equation. Y equals, and a is 1/2, and b is 4, and that goes in parentheses and then raised to the x. The 1/2 is not being raised to the x, only the 4. And so for that reason, you cannot multiply that half and that 4 together, ever. This one has to stay separate from whatever the a value is in front of it, because only the b value is being raised to the x power. So that's very important, that you don't separate them and you don't multiply them together. All right, well, I'm going to end this video, and then there's going to be another one that I'm going to have y'all watch tomorrow. So here's a joke, since I know y'all love them.
You heard it long?